Hello, my good friends. My name is Teteje Kepsi Richard, and welcome to my online tutorials. Our discussion on numerical and computational method today will be on forward difference, backward difference, and another operator, which is the shift operator. So before the video ends, we'll look at the relationship between the forward difference and the backward difference, as well as the shift operator. This will be very interesting engagement, so please be my guest. So when you meet these signs, you take notice of this is the forward difference operator, which is known as delta, and this is the backward difference operator, that's the nabla, and this is the shift operator. So anytime you see them, this is the forward difference operator, backward difference operator, and then the shift operator. I hope you get that. So remember when we're doing the shift or the forward difference operator, we said del y naught is equal to y1 minus y naught, if you remember very well. So we can say that the delta of a function, okay, is equal to a function that is greater than the function that is greater than it, but next to the function minus the function itself. So a function that is greater than this function will be f of x plus h, where h is the difference between those two functions. Maybe if this is 2, this is, if this is 2, this is 1, if this is 3, this is 2, when the difference is 1 in that order. So we can say that delta of a function is equal to a function that is greater than it minus the function itself. I hope you get that. The same way, if you want the delta of f of x plus h, we can say that a function that is greater than f of x plus h, that will be f of x plus 2h, that's the next one, minus the function itself, f of x plus h. I hope you get that. The same way, if I want to find delta of a function of x minus h, it will be equal to a function that is greater than this function will be f of x. I hope you know that. Then minus the function itself, that's f of x minus h. I hope you get that. So this is how the forward operator works. Now what of the backward difference operator? So the backward difference operator, which is nabla. Remember we said nabla of y1 is equal to y1 minus y0, if you remember very well. So we can conclude that the nabla of a function, okay, is equal to the function itself minus a function that is less than that function. That's f of x minus h. So we can also say that the nabla of f of x plus h, okay, will be equal to the function itself, which is f of x plus h minus a function that is smaller than this, which is f of x. I hope you are getting that. So another way, if we want to find the nabla of a function of x minus h, so it will be equal to the function itself, f of x minus h, minus a function that is smaller than it, which is f of x minus 2h. I hope you get that. So please, this is how the forward difference operator and the backwards difference operator works very well. Now, let's look at the relationship that occurs between the forward difference operator and the backward difference operator. So we have a question here. The question says, prove that delta nabla, that's delta times nabla, is actually equal to delta minus nabla. That's I. And I. Delta over nabla minus nabla over delta will be equal to delta plus nabla. So how do we solve that? We are just going to use the relationship between them to solve that. So the first one, we say we should solve that delta nabla is actually equal to what? Delta minus nabla. So what I will do is that I will try to multiply a function by it. One side, so I will use one side to prove that the other side is correct. So you can use this to prove this is correct, or use this to prove that that is correct. So I will just multiply this function by f of x. So this will be equal to, remember, delta. And what is nabla of a function? Remember, the nabla of a function, f of x, is the function minus a function that is smaller than it. So we can say this will be equal to, so nabla of a function will be f of x minus f of x minus h. I hope you get that. Now we can expand. So we can say the nabla, the delta nabla of a function, okay, will be equal to, now I'll expand this. That's delta of the function, then minus delta of the function x minus h. So we can say delta nabla of a function is actually equal to, so what is delta of a function? Remember, delta of a function is a function that is greater than it minus the function itself. So we can say f of x plus h minus f of x. I hope you get that. Then minus, what is nabla, a delta of a function x minus h. Delta of a function x minus h is a function that is greater than it minus a function. So f of x minus f of x minus h. So say f of x, then minus f of x minus h. I hope you are getting that. So having known that the delta of a function is a function f of x minus h minus the function itself, then my f of delta of s, f of x minus h is f of x minus f of x minus h. Then what is a function x minus x plus h minus f of x? So you come here, look at it, f of x plus h minus, so we need f of x plus h minus f of x. So that's what is delta of a function. So we can say that delta nabla of a function is equal to, this one is actually delta of a function. Then this, look at this, a function, the function, which operator that we have, the function is a minus a function that is greater than, smaller than it. So look at it. Nabla of a function is a function minus a function that is smaller than it. So we can say the whole of that is what? Is nabla of a function. I hope you get that. So we can say delta nabla of a function is equal to, what is common to them? A function is common to them. That will be delta minus nabla, all in bracket, times the function. So we can divide both sides by f of x. Then we can say delta nabla is equal to delta minus nabla as required. This is very interesting. I hope you get that. So we know that delta nabla is actually equal to delta minus nabla. We use that idea to solve the second one. So solve the second one, which is delta over nabla minus nabla over delta is actually equal to delta plus nabla. So what we do, I will use this side to prove that this is correct. So delta over nabla minus nabla over delta. So I'll find the LCM just like with solving fraction. So the LCM is nabla, delta nabla, or nabla delta is the same thing. When nabla goes here, divides this, we have delta. Delta times this will be delta square. I hope you get that. When delta go here, we have nabla. Nabla times nabla will be nabla square. Now what is this? This is difference of two squares. So we can say, so we have this delta square minus nabla square is actually delta plus nabla in one bracket. Then another bracket, delta minus nabla. Since that is difference of two squares. All over, remember we proved delta nabla. And delta nabla is actually delta over nabla. So we substitute that. That will be delta minus nabla, actually. So this will divide that. What is left is delta plus what? Nabla. So we can actually say that delta over nabla minus nabla over delta is actually delta plus nabla as required. This is very interesting. Very, very interesting. We'll solve more examples on this so that you'll be abreast with the concepts. There is another question also here that if the interval of difference is 1, we should prove that the delta of 2 exponent x or all over x factorial is actually equal to 2 exponent x bracket 1 minus x all over x plus 1 factorial. So how do we solve that? Remember we said that the delta of a function is actually equal to a function that is bigger than it, then minus the function itself, where h here is the interval of difference. So the interval of difference here is 1. So we can say that this, the delta of this function, that's the delta of 2 exponent x over x factorial is actually equal to, now in place of x now we substitute x plus 1. So that will be 2 exponent x plus h, sorry. So x plus 1, h is actually 1, over x plus h factorial. Then minus the functions, and the function itself is that. So 2 exponent x over x factorial. I hope you get that. Remember, we said the interval of difference is 1. Then we can say this is actually equal to 2 exponent x plus 1 over x plus 1 factorial, then minus 2 exponent x over x factorial. So you get that. So remember, x plus 1 factorial can be x plus 1, then times x minus 1. Remember that. So we said this is equal to, that's nabla, delta of 2 exponent x over x factorial will be equal to 2 exponent x plus 1 over x plus 1 times x factorial. I hope you get that. So we don't know the limit, so we can't be continuing like that. So we say minus 2 exponent x over x factorial. Now we can rewrite this as, using this is 2 exponent x then times 2 exponent 1. So we can say that the delta of 2 exponent x over x factorial will be equal to 2 exponent x times 2 exponent 1. I hope you get that. Using this is all over x plus 1 then x factorial minus 2 exponent x over x factorial. Now what is common to these two terms? We have 2 exponent x over x factorial is common. So we can say that the delta of the function 2 exponent x over x factorial will be equal to 2 exponent x over x factorial bracket. What will be left here? Will be left with 2. 2 exponent 1 is 2. 2 over x plus 1, then minus. The whole of that is out, so minus 1. Now we solve this. So we have this is equal to 2 exponent x over x factorial, then times the LCM is x plus 1. When x plus 1 go there will be 1 times 2 will be still 2. Then this is over 1. 1 divided it will be that. So that will be x plus 1. I hope you get that. So this will be 2 exponent x over x factorial times 2 minus 2x minus 1. I'm expanding this. 2 minus x, then minus 1 all over x plus 1 for the bracket. So what do we do? We solve that. So we get 2 exponent x over x factorial bracket 2 minus 1 will be 1. So 1 minus x all over x plus 1. So we can simplify further and say the nabla the delta of a function over x factorial will be equal to 2 exponent x times 1 minus x over, I can write this as x plus 1 times x factorial. And remember, this x plus 1 times x factorial is actually x plus 1 factorial again. Remember, it was like that before we rewrite this. Then we can say that delta s exponent n over x factorial is equal to 2 exponent x 1 minus x all over x plus 1 factorial as we are required. I hope you get that. So this is how the forward difference operator and the backward difference operator works. Now, we'll see how the third operator, which is the shift operator, how it is related to the forward difference operator and the backward difference operator. So remember we said that the delta of a function is a function that is greater than it minus f of s, where h is the interval of difference, and the number of a function is a function itself minus a function that is less than it. So what is the shift of a function? That's a of a function. The shift of a function is actually equal to a function that is greater than it. Very, very simple. I hope you get that. So now let me find shift of both sides. So we can say that shift, I'm finding shift of both sides, the shift of a function of both sides. Okay, this will be equal to of a function x plus h. So if this multiply this, we can say this is e exponent 2 of a function. So the shift square of a function is actually equal to, we say a shift of a function is just actually a function that is greater than it. So we can say x plus 2h. Are you getting it? So it simply means that anytime we find e exponent 3, that's the shift operator exponent 3 of a function, it will be equal to a function that is greater, it will be equal to x plus 3h, like that. So in that order. So we can say that, we can conclude that e of a function, e exponent n of a function is equal to f of x plus nh. That means any place you see n here, and you multiply by the h there. I hope you get it. So we can also say that the e of negative n, e exponent negative n of a function is equal to f of x. Remember the n is negative n, so minus nh. I hope you get that. This is very, very interesting. Very, very interesting. So now we see the relationship between the shift operator and the forward difference operator, as well as the shift operator and the backward difference operator. So remember we said delta of a function is equal to a function that is greater than it minus the function itself, where h is the interval of difference, and the shift of a function is equal to a function that is greater than it. Can we see any relationship? You can see that this here is just the shift of a function. So you can say delta of a function is equal to the shift of the function minus the function. I hope you get that. So in place of this, I substitute that. So we can say delta of a function is equal to what is common to them. You can say f of s is common to them. We can factor out. So we say e minus 1 f of x. Okay. When we divide both sides by f of s, we can say delta is equal to the shift minus 1. I hope you get that. So this is a relationship between the delta and the shift. Or we can say the shift is equal to delta plus 1. This is very interesting. Very, very simple. So this is the relationship between the shift operator and the forward difference operator. Now we see the relationship between the shift operator and the backward difference operator. So remember we said the number of a function is actually equal to the function minus a function that is smaller than it, where h is the interval of difference. Very, very important. So now how can we generate or formulate the relationship between the backward difference operator and the shift operator? So remember we said that, look at this. We said that the shift operator exponent negative n of a function is equal to x minus f of x minus nh. So you can say then of negative n of a function, you and I developed that, will be equal to f of x minus n of h. I hope you get that. So we can say that e exponent negative 1 of a function will be equal to f of x. In place of n now we substitute 1, so minus h. I hope you get that. So in place of f of s minus h here, we substitute this. So we can say that the nabla of a function f of x will be equal to f of x then minus e exponent negative 1 f of x. I hope you get that. So nabla of a function, so what is common? The function is common, so we factor it out. So 1 minus e exponent negative 1 f of x. So we can divide both sides by f of x. We can get nabla is equal to 1 minus e exponent negative 1. As so what we do, we can bring e exponent negative 1 here equal to 1 plus nabla. So when nabla goes there, down, it will rather be minus. So e exponent negative 1 equal to 1 minus nabla. We can find e exponent negative 1 of both sides. So that will e exponent negative 1 or exponent negative 1 equal to 1 minus zeta or exponent negative 1. When we do that, this multiply this, it will be 1. So we can say e is equal to 1 minus nabla or exponent negative 1. I hope you get this. So this is the relationship between the shift operator and the backward difference operator. We'll end it here today. Please remember to subscribe to my YouTube channel before you sign out. This will make YouTube promote my YouTube channel or videos, and I can record more mathematical content for you. Until we meet again, my name is algebraic.